Alright, let's talk about solution redox reactions. Unlike the single displacement reactions or even combustion, if you look at combustion reactions, you realize they're also redox reactions in and of themselves. We have reactions where we can actually perform the entire thing in water. And the thing about water is that it's not an innocent molecule, it's not a spectator molecule. In the course of a redox reaction, water can actually get involved in the reaction itself. And the reason why is because water has this autoionization characteristic to it. So in some amount of water, you're going to have a small amount of H plus hydronium present and some amount of hydroxide. And all these species are definitely easily involved in redox events. So now you have three partners that could actually play a role. And so the way in which we go balancing redox reactions that are in solution is a little bit different than your typical single displacement reactions, decomposition, synthesis, or combustion, where you basically can solve them by inspection. Here, you cannot do that. You have to follow a method to balance the reactions. And the method consists of a number of steps. In the first step, you basically balance anything other than oxygen or hydrogen. As long as it's not oxygen or hydrogen, you can balance it the regular way by inspection. But then, what happens at that point is that we need to balance the electrons, and this can be done via a number of different ways. But ultimately, what we'll have to do is balance oxygens with water, which is a very unusual way of balancing a reaction. Basically, we're going to be introducing molecules that won't be present in the original reaction to begin with. But we'll have to do that because water can get involved in the redox reaction itself. And so if we have a lack of oxygens, we will have to make up that number of oxygens of whichever side is lacking it by adding enough waters. And at that point, we have to balance the hydrogens on both sides by adding H pluses, not H's, not H2's. It has to be H plus specifically because that's the partner that you get from the auto dissociation of water. Alright, so we're going to do this via the half-redox method. There's actually two different ways to do it, but in this class, I'm going to stick to just the half-redox method. It's a little bit of a procedure, but it's not a terrible procedure. So hopefully you'll be able to follow this. So what happens is that you have two reactants present and you have two products. That's one characteristic way in which the equation can present itself. Now, what needs to happen is that the elements of the same kind, so if you look at this, you have chromium on the left side, you have chromium on the right side. You also have vanadium on the left side, and you have vanadium on the right side. So elements of the same type, other than oxygen and hydrogen, you want to basically split them up into two half-redox reactions. So this is the true path that we're going to follow to balance the equation. We're going to first break up this into two halves. First, we set it up so that the chromiums are by themselves, and in the second reaction we have only the vanadiums. Now notice that dichromate and vanadium, which were in the reactant side, are still on the reactant side. You don't change the order, right? If something was a reactant, it still needs to remain a reactant, and if something was a product, it still needs to remain a product. Alright, what we do now is we balance all the non-oxygen, non-hydrogen atoms. That's to say that the chromiums and the vanadiums need to be balanced in this equation. And if you look carefully, you'll see that you have two chromiums on the left side of the first equation, but only one on the right side. So you'll need to multiply that by 2 to balance the non-oxygen, non-hydrogen atoms. Vanadium, we only have one on the left side, one on the right side. This is balanced. Alright, here is where we start looking at the oxygen. And if we have any discrepancy in the amount on either side, we will make that up by adding enough waters. So looking at the first equation, we're dealing with 7 oxygens. The right side doesn't have any oxygen, so what we'll do is add 7 waters. As many waters as you do need oxygens. And the same idea for the second equation. We have 2 oxygens on the product side, none on the left side, so we're going to add 2 waters to the left side. Alright, so 7 waters on the first reaction on the product side, 2 waters on the left side for the second reaction to balance the oxygens. Undoubtedly, at this point, since we have added water, we have introduced hydrogens. So now we need to take care of the hydrogens. In the first equation, there's no hydrogens on the left side of the equation, but on the right side, we now have 14. 7 times 2, giving you 14 hydrogens. If any of the other molecules were to have hydrogens, don't forget to include those hydrogens in the total count, because at the end of the story, you still need to balance all of the atoms. All right, so we have 14 hydrogens on the right side of the equation, none on the left side. We're going to have to add 14 H pluses specifically, okay? So we're going to do this thing here. We're going to add H pluses to balance the hydrogens. And over here, we have 4 hydrogens on the left side, none on the right side, so we'll have to add 4 H pluses on the right side. So there it is, 4 H pluses, 14 H pluses. Okay, now what happens is that after you have balanced the hydrogens, the oxygens, and the non-oxygen atoms, now we need to assess how many electrons are being lost and or gained in the processes. So the way we're going to do this is by looking at the charges on both sides of the equations, the overall charges. And we'll basically have to ensure that the charges are the same on both sides. There's a very simple way to do that. First, let me make a little bit of room right here so that we can do this relatively easily. We take a look at dichromate. There's only one dichromate, and that one dichromate has a charge of 2-, so that's a 2- charge. We have H plus with a charge of +1, but there's 14 of them, so that will give you an overall 14 plus charge, which if you add them together will give you overall 12 charge on the left side. Here on the right side, water doesn't have a charge, so it doesn't really affect the charge whatsoever, but chromium 3 plus does have a charge. There's 2 of them, so that gives us a +6 charge overall. Down here, neither water nor vanadium have a charge, so the overall charge is 0 on the left side. On the right side, VO2 has a +1 charge. There's only one of them, so that gives us a +1 charge. And there is 4 H pluses with an overall contribution of +4 for the charge. So altogether, we have +5 as the overall charge on the right side. So it's important that you keep in mind that you're only looking at the overall charge of the entire species, right? So I'm not looking at the charge of just the chromium or the charge of just the oxygen. It has to be the charge of the entire dichromate for you to do this. Same thing for vanadilyl, same thing for Cr3+. Alright, so now what happens is that all you really need to do is subtract the two values. 12 minus 6 is 6. 5 minus 0 is 5. And, you know, if you do this, all you really need to do now is place that number, that discrepancy, right? 12 minus 6, which is 6, is really 6 electrons that you're missing. And the 0 minus 5, which is, well, once you take the absolute value, which is 5 electrons, that tells you that you're missing 5 electrons altogether. And all you really want to do is place the electrons on the side that has the highest charge. So between 12 plus and 6 plus, 12 plus is the highest charge. So the 6 electrons, you want to place them on the left side of the equation. Down here, between 0 and 5, 5 is the highest charge, so you want to place the 5 electrons on the right side of the equations. So we simply do that. We add them in that specific order. So just remember, subtract the overall charges and add the electrons to whichever side had the highest charge to begin with. What you should find out at this point is that for one of the equations, you have electrons on the left side of the equation. For the other equation, you have electrons on the right side of the equation. And this need not be in this specific order. You could have had electrons on the product side for the first one and on the left side for the second one, right? That depends on how you arrange your half reactions. But the one thing that will be true is that one equation has to have electrons on the reactant side and the other one has to have it on the product side. All right, now what we need to do is balance the number of electrons. At the end of the day, you have to have the same number of electrons on both sides because whatever electrons are getting lost in the oxidation have to be gained in the reduction. All right, so that tells us that, well, we have 6 electrons here, 5 electrons there, and I get rid of the fluff so that we can see clearly what's happening. So what you want to do is cross multiply the numbers. We want to multiply the top equation by 5 to make the number of electrons the same. We want to multiply the equation on the bottom by 6 to make the electrons the same. By the way, when it comes down to this particular step, you still have to go with the lowest ratio. So if it was possible that the 5 and the 6 could have been reduced to lower numbers because they share a lower common denominator, then you have to go with the lowest ratios. So for instance, if this number was a 10 and that was a 12, because that's how many electrons we had here, then you will have to reduce the 10 to 5 and the 12 to 6 to get to the lowest ratio. So here's something to keep in mind. In this case, 5 and 6 cannot be reduced any further, so literally we're just cross multiplying the equations. So what you end up doing now is factoring in the 5 into not only the electrons but also each individual reactant and each individual product. And the same thing goes for the 6. It gets distributed to each of the individual components in the equation, reactant and product side alike. So we will multiply 5 by 1 dichromate, giving us 5 dichromates. We will multiply 5 by 14 H pluses, giving us a total of 70 H pluses. 5 times 6 will give us 30 electrons. 5 times 2 will give us 10 chromium 3 pluses, and 5 times 7 will give us 35 waters. And the same thing goes for the second equation. Multiplying everything by 6 will give us a total of 12 waters, 6 vanadiums, 6 vanadiols, 24 H pluses, and 30 electrons. So notice now that the electrons are balanced. And at this instance, what you should have is all the non-oxygen atoms balanced, all the oxygen atoms balanced, all the hydrogen atoms balanced, and now the electrons are balanced. So the moment all of that has been taken care of, you can now add both equations together. And the one thing to keep in mind is that if you do have waters on both sides, you gotta cancel them out uh, to the greatest extent possible. And the same thing is true for H pluses. If you do have H pluses on both sides, you have to cancel them out to the greatest extent possible. So between 30 electrons on the left side and 30 electrons on the right side, well, they fully cancel out, as they should. We made sure that that will happen by balancing the equation. But then looking at the protons, we have 70 H pluses on the left side. We have 24 H pluses on the right side. So that means that we need to subtract 24 from both sides. And the same thing goes for water. We have 12 waters on the left side, 35 on the right side. So we need to subtract 12 waters from both sides, meaning that we'll end up with 23 waters on the right side. And on the left side, we're going to subtract 24 from both sides to yield 46 H pluses. And at this point, you add everything together, meaning that you combine all the reactants and keep them on the reactant side. You combine all the products, bring and keep them on the product side. So we'll have 5 dichromates plus 46 H pluses plus 6 vanadium zeros, all on the reactant side. On the product side, we'll have 10 chromium 3 pluses plus your 23 waters plus 6 vanadiols, and that's pretty much the end of the story. So you just bring it all down, and at this point your equation should be balanced. And by the way, the order doesn't necessarily matter as to how if the chromium comes first, if the vanadiol goes last. It doesn't really matter, although I may tell you on some of the problems on Canvas to place them in a specific order, like say chromiums first, then vanadiums, then anything else. I may tell you that, so keep attention. Keep in mind that I can give you specific ways in which to write it down, because otherwise the number of options becomes a little bit overwhelming for me. But all right, so this is the half-redox reaction. So I'm going to do one more example, but I'm going to save that example for the next video. So I'll see you in the next video.